So, welcome everybody. It's my pleasure to welcome Elias Holm, who graciously came down to, interrupted his vacation no less, to come see us to talk to us about background humidity errors. So, just a quick bio, as we do in these things. Elias has a PhD from the University of Stockholm, having left his native Iceland to study there in numerical methods. He spent a brief amount of time at KNMI. He doesn't want me to elaborate on that. And now, and since 1996, he has been working at ECMWF on data analysis. And I'm going to hand over to Elias.
Okay, thank you, Antti. I mean, thanks for having me. I got a very intriguing email from Andy. He was talking about what does ECMWF do for humidity in the stratosphere. I was thinking, well, we don't know anything special at the moment. So I was thinking, well, but what would happen if we would do it? We had done that experiment many years ago, but now I decided let's try that again. So I will come to that at the end of this talk. And we've been discussing that today, some of the stratospheric analysis with some colleagues here. But what I'm going to present here are some of our latest developments in humidity background errors and what we're up to next, and then come back to the stratosphere at the end. So there will be three short topics here. So next one, yeah. You see that now? Okay. Let's go to the next. First, just a short background on how we do our background errors in general. So we run an ensemble of data assimilation. And every day we calculate a covariance matrix of the day. This EDA has 25 members. They are at 80 kilometer resolution. Our operational model is at 9 kilometers. So this is at half the operational resolution. And we really need to have this high resolution in the EDA, because otherwise it won't capture really the weathers that we care about. It won't capture tropical cyclones. With 80 kilometers, we capture tropical cyclones, for example, reasonably. They're not going to be 100% realistic, but they are as good as one could expect. And they are in the same ballpark as the 9 kilometer model. That's very important for us. So from the EDA, we calculate two things. We get the standard deviations. And these are just the pure standard deviations of these 25 members. We filter them slightly for noise, but these are fully flow dependent. On top of that, we got three-dimensional correlation matrices of the day. They are not fully flow dependent, but partly. So for the very low wave numbers, we mixed in up to T63 about 70% from climate. This is just an annual average from the EDA variances, or EDA covariances. And then we gradually, as we go to higher wave number, we gradually go to the errors of the day. So when we go to T309, we are already at 90% plus from the errors of the day. So just to give a background how this looks like, let's have a look first here. Here are the scales for our four fundamental variables, sun and average. I showed just from 100 hectopascal down to the surface. Of course, we've got stratosphere as well, but we're just focusing in here on show the general feature. So we got vorticity, unbalanced divergence, unbalanced temperature, and unbalanced relative humidity. So these are our control variables. We see here for vorticity, it peaks out at about 80 kilometers, the length scales. Of course, we get up to a couple of 100 kilometers in the stratosphere. Divergence is a bit lower, maybe peaks at about 60, 70 kilometers, horizontal length scales. Temperature, of course, we are up to a couple of 100 kilometers. And relative humidity, actually, in the upper troposphere, it's about peaks at about 134 kilometers. So actually, people would say which variable has a shortest length scale, and in actual fact, it's not humidity, it's more the vorticity, I would say. Okay, next one. So now we're going to look at the standard deviations. Same thing, zonal average, vorticity, divergence, temperature. And here, instead of humidity, I showed this for the Q divided by Q background. So this is in percentage. So this peaks at about 100, at about 50% here. I did it like that because otherwise there's too much variation in the relative humidity errors from the here that you wouldn't see the whole picture. It's nice here that we see in vorticity, Tropics, and in humidity as well. Let's go to the next one and have a look at the increments from this. Again, the zonal average increments for the same day. Vorticity, divergence, temperature, and humidity. And here you have a part of the answer what to do with stratospheric humidity, what Andy asked me about. So you see that we had variances from the previous plot, which went all the way. These were the variances from the EDA. But actually what we do in our analysis, because there's not much information on humidity above there, we do taper off the background errors that they actually use around the tropos, actually around the hydropause. So there end to be no actual humidity increments above there. And then, of course, humidity changes there, but it changes in response to changes in transport and changes in temperature for the rest of the assimilation. Okay, next one. This is just a 200 hectopascal, how it looks in horizontal for the length scales. You can see a little bit in the upper troposphere, 200 hectopascal. The length scale have about the same pattern for all variables. You see here like downdraft regions, and then there's quite a contrast between the ocean and land. You will see that further down. Again, let's go to the next one. This is the standard deviation at 200 hectopascal. You start to see a lot of detail here. Let's go to the next one. Now we're down at the surface, length scales again. The maximum here is at like 110 kilometers, and most of the length scales here in the dynamic fields are at about 40 to 60 kilometers. In temperature, of course, we are up to 300-400 kilometers, where it is maximum. What is nice here, when you look at humidity, relative humidity, it's not surprising this being relative humidity, it's quite related to the temperature. And again, here you can see very sharp contrast between land and sea. For example, if you look here over South America, the variances change, or the length scales change very rapidly. Just to tell you a little bit more detail, the way we do the length scales, we do calculate covariance matrices in 250 by 250 kilometer boxes. So we average all the samples in there for those. And then when we need a covariance matrix at any point, we interpolate linearly, bilinearly between the closest covariance matrices. That seems to be good enough. But we really need to sample over this 250 by 250 kilometers to get some noise out of the system. Okay, next one. These are standard deviations. Okay, so that was it. So this is more or less what the EDA does for us. Let's now look at the humidity in more detail. So humidity background errors, there's a bit of story to this. The length scales in correlation matrices we have been using for the humidity since we started using the ETA. But for the variances, we were a bit conservative, and we were only bringing the variance in step by step. Previously, what we did, what was in operations up until July 2017, was like this: that we did have flow-dependent formulation for the humidity variances, but it was based on, let's say, what's the climatological average variance for a given model level, a given relative humidity. That gives you a lot of flow dependency, but it gives you climatological average flow dependency. So it's never going to capture the extremes. It's not too bad though, because for the background errors, it's actually better to have too small background error than too large. So our error was on the safe side, so to speak. But from July, we have now brought humidity to the 21st century as well, and we are taking the variances straight from the ETA. And this seems to work surprisingly well. And what this does, I mean, just we see that the microwave infrared data, they get used better. All humidity data get used better. Because of this, for radiuses, we split the humidity, we split the signal into humidity and temperature more accurately. And this has quite an effect on the winds in particular, particularly in the tropics actually. We see that this thing just makes the humidity analysis or humidity fields that little bit more accurate, so that the winds, the tracing effect of 4D bar catches onto this and really forces the wind to adjust to this. So that has been quite beneficial for the wind, this change in particular. And when we look at the results of this, we had quite good impact on scores in general, northern hemisphere, southern hemisphere, tropics, in particular the winds in the tropics, I would say. Let's have a look at the next plot. So this is just before and after. So these are the humidity variances before with the climatological formulation and after. I'll show you a more detailed picture later, so don't stay about the details. But what you can see here is that in the tropics, things are more or less the same ballpark. But when we come to extratropics, there is a lot of variability. We get up to about twice as large variances now with the humidity. Because what we were doing before, for any given humidity relative humidity value, we've averaged together a lot of situations. But here, of course, you have a particular front coming in, and then you have a higher variance for that particular relative humidity value, higher level of uncertainty. So let's look at the next picture to see this in more detail. So here you can see how it works. So here we have two tropical cyclones, Irma and Jose from 8th of September. And here we have the old and new formulation of the humidity variances at 500 hectopascal. You can see that both capture more or less the same thing. You can see the cloud band here, you can see increased variances. You can see the tropical cyclones in both. But again, what you see here is that in the old formulation, you don't capture the extremes. It just captures what the average error would be for such a relative humidity. But now, of course, with ETA, you've got it as it should be. So we get the actual increase in errors where they should increase. Of course, this looks a little bit wobbly, but again, that is because in practice we need to wavelet filter things for the signal to noise ratio. So that is also a very necessary step. We can't just take the raw. We can sort of take the raw radiuses, but again, raw variances. But again, to be on the safe side, we don't do that because we see that when we go to tropical cyclones, we may get too much of the good. The background there may be too good, so that any observation which comes in error may derail the system. So really, one of the reasons why we can't allow absolutely the full amplitude of the background errors in tropical cyclones is to make it more robust against observations that pass our variation quality control. If you get a drop zone, which even if you try to treat it perfectly, comes through and passes our quality controls, it can really destroy the tropical cyclone if the background error is too large. So we need to be conservative because of that. Okay, let's go to the next. This is how now how the humidity data are affected. So here we see that humidity is really improved, and this is fit to AMSR2. This is against an own analysis. This is against the first guess, and this is improvement. So you can see that you see that they're fitting observations better here because the errors are larger. That by itself doesn't help us, but this does because we see here that really the first guess fit is better. So there is a real improvement in the short range forecast, which fortunately translates into the long range as well. Let's look at the wind.
So could you just tell us what these channels are sensitive to, for those who don't know?
These are water vapor channels, most of them.
Okay.
So 7, 8, 9, 10, 11, 12, 11, and 13. Now, I'm not an expert of AMSR2, so I cannot tell you exactly where they peak these channels.
Okay.
But I've been told these are water vapor sensitive channels.
Okay. They're all on the 1.86 gigahertz line, presumably.
Something like that.
Yeah. Okay, sorry.
So, but the point is, it looks like this in all radiances. You can take any radiance, which is any kind of sensitivity to humidity, it looks like this for all of them. All wind sensitive observations, all humidity sensitive observations, it's all improved. First case fit. And this is quite nice, this is another global picture for the satellite winds, atmospheric motion vectors. Here you can also see the first case fit. And that actually gets better the higher up you get. So we're quite happy with that, and I think this was a relatively simple change with a lot of impact. Okay, let's go to the next one. So where do we go from here? So just gonna show you now a couple of things which we've been thinking about for a while, but which are now trying to test and get further with. That is actually, we've got the balance operator, but in actual fact, humidity, you can also see as a part of the balance operator, because humidity errors are correlated with temperature errors. Temperature errors are correlated with dynamic errors. So altogether, one thing which we don't have in our system at the moment is a coupling from the humidity, taking explicitly into account the coupling between the humidity and the dynamics. And what we have in our current system is this thing in blue. This is more or less a description of our control variable, which is more or less a relative humidity. It just says that humidity increments are some of our unbalanced increment from our unbalanced control variable, plus some contribution, which only is on if CP is positive. CP, that's the background cloud. And we don't want to mess around with the background cloud in our analysis. So what we do is that we have a statistical regression, which determines once and for all. It's very accurate, because that's how the physics is actually built up. So we can have this as a function of relative humidity. This just goes more or less from 0 at 80% relative humidity up to 1 at 100% relative humidity. So you can say as a function, if the relative humidity is large, there is a correlation with temperature because of condensation. And this is what we had in our system. Now, of course, if you're condensation or evaporation, really, temperature should change as well. So that's what we're now experimenting with, adding this total saturation adjustment with temperature in. And if you change humidity in moist regions, then cloud condensation should also change. And so the complete picture is given by these three equations here. Given a vector form down here, we're going to split cloud condensate into liquid and ice. So with this formulation, we can expand our current formulation, which is this, to take this into account. So we have a coupling between temperature and water vapor. So even a pure water vapor increment affects the temperature directly. And then we can expand to this here, And this is something which we're interested in because we see that we do need to account for cloud condensate in the control variable because we got upper peaking, so high peaking channels. These are sensitive to ice in the microwave, for example. And this is, so in our 12-hour assimilation window, this signal can be quite long-lived. So for optimal assimilation of these observations, we really need to include these guys. Okay, let's go to the next slide. This is just a couple of the details here. I'm not going to bore you with things in detail here, but some of the assumptions that we have to do to get this formulation which I showed you on the previous page. Let's go to the next one. But I want to put this in context now. Get this in context with the dynamics. So where does this fit in? So you may or may not know, I think John Durbin knows very well, because he is the one who originated this. So we have our balance operator consists, we have a horizontal nonlinear balance, we have some vertical statistical regression, and we have some quasi-geostrophic omega equation. So these guys together couple the temperature, you have hydrostatic balance, and you have divergence, and you have vorticity. So vorticity is the primary driver here, and you get balance increment in temperature, surface pressure, and divergence from vorticity increments. Okay, that's it. So we want to link humidity into this picture. Let's look at the next slide, how we do that. So this is the vertical balance, this nonlinear dynamic balance. Then, out of that, we come in with unbalanced divergence, unbalanced temperature increments. We get some updated divergence in temperature increments. And then the next step would be to take that into omega equation and get a further contribution to the divergence. So the divergence would adjust in response to temperature changes. But what we can do now to make, let's say, some kind of a linear diabatic balance, and in a simple way as possible, we can of course couple it in a full equation, everything together, but I think this captures the essence of it anyhow, is that we do the nonlinear balance, we get the temperature out of there. Here we do this diabatic adjustment, and in here, temperature will now change in response to changes in humidity and cloud condensate in cloudy regions only. This fully adjusts automatically to cloudy regions. It will do nothing outside cloudy regions. Assuming you have the cloud in the right place. We do not always have, but well, it's not perfect. Okay, so now this comes in as input there. So now we have an adjusted temperature. So now the omega equation will adjust not only for temperature changes, but also changes in humidity and cloud condensate later on. Let's go to the next slide. So this is the whole thing written out. But the trick is we adjust the saturation adjustment, we apply the saturation adjustment just before the omega equation. So then the final divergence will dynamically support changes in water vapor and cloud condensate without any spatial treatment. And this matrix here, blue is what we already had, and red is what is added with this change. The nice thing about this thing is that the last line, this is cloud condensate, you can strike out completely without changing any of the rest of the formulation. That means that you can implement it first, just having the temperature humidity adjustment, and then when you got a control variable for cloud condensate, you can add that on. It doesn't change the formulation for the other two. So let's go to the next. So this is an example of how this looks before and after. I'm showing here the increments from an all-sky profile or all-sky observation microwave. On this side here, you got cloud in here in yellow, and then you got the temperature increments in red, and water vapor increments in blue. So there's positive water vapor increment and negative water vapor increment. And you see the wind, if you stare, you see wind increments as well. Some very, very weak wind increments here. But if you now apply, well, you do the saturation adjustment for temperature, so you get temperature increments in response to water vapor as well. And you apply it before the omega equation. Then you get, of course, the increments, they do change, of course. But the important part is that you do get now the wind shears. Here you see the vertical and horizontal wind together. So that is really the adjustment in the circulation caused by the change in divergence. So this is our next improvement that will add up on top of what we did before. See how that goes. Okay? And after that, we will do the cloud, liquid and ice. That's all in the pipeline for the next year or so. Okay, let's go to the next topic here, close to our heart. The final thing is about stratospheric humidity analysis, off or turn it on. So this is one of the things that you sweep under the carpet, all of us in one way or another. You don't really know what to do with humidity. So this is a story behind it, why we do this at ECMWF at least. So at ECMWF, when we looked at the situation years ago, we had long-standing issues with model biases in the low stratosphere. The model biases. And they would get just worse if we would start to assimilate radiance information there. That was the first step. Second thing is that when we looked at the humidity channels that are giving information in the stratosphere, I mean, these are peaks in upper troposphere, mid to upper troposphere. But then it's the tails of the Jacobians that come into the stratosphere. So the amplitude of the tail is maybe 2 orders of magnitude smaller than the peak. But humidity up there is also 2 orders of magnitude smaller. So it's a real signal. So we have a problem then that any inaccuracy in the upper troposphere, some small adjustment by bias corrections, which give, let's say, a residual signal in the upper troposphere and are of no importance there, may translate into systematic increments in lower stratosphere through the tail of the Jacobians. And this in turn starts to change the water vapor. The water vapor interacts with the radiation. That changes the temperature, and we end up the 10-day forecast, which is worse than before. That's the official story, and why we, let's say, decided many years ago that we taper off humidity background errors so we don't allow any humidity increment directly in the stratosphere. But then Andy sent me an email and asked, so what do you do in the stratosphere? And I said, we do this. And then I said, hey, I haven't done for many years the experiment where we turn it on. So so out of curiosity, you go to the next slide. Okay, yeah, this is a good one, just before I go to the curiosity thing. This is the YASI. A few channels, not necessarily channels which we use, but these are water vapor sensitive channels. You see they're peaking here at 2, 3, 4 hectopascal. You see these tails up here. And this is really the issue, that you're assimilating something here, bias correcting in here, and then you've got a couple order of magnitude less water vapor, which is being affected up here. And the issue is really, you're doing something sensible here, and what happens there has no effect on this, but what happens here is more or less a residual of the corrections down in the upper troposphere. So it's a bit of a random function where we end up there. Of course constrained by the model, but If you're lucky, it goes in the right direction. Next one. So I did the following experiment. I mean, with the formulation we showed you before for the humidity variances, we now got the EDA relative humidity variances everywhere, of course. So I just use these variances everywhere, and we start the assimilation experiments. I mean, nothing dramatic happens. It doesn't misbehave or anything. It looks fine. But here I show you on the left model level, 100 hectopascal model level. This is a cross section from south to north. And what I show you is a ratio of the current humidity in the experiment with humidity on with the reference experiment with humidity analysis off in the stratosphere. And you can see that things start to change here. And if you make a cross section here, or actually an average between 25, 50 and 25 north, look at this, you see that in vertical it's really grown to an extent. And you see the experiment when I left on Friday, it had done about 40 days. So this was down to about 30% reduction in humidity. All good so far, because we happen to have a bit of an overestimate in lower stratosphere. But if we had an underestimate, this would not have made anyone happy. So let's go to the next one. Final one. So this is just the evolution over 10, 20, 45 days. This is really what is happening also. We see that things are actually, there are two processes going on here. First is, we got humidity increments directly from below. The second process is, we get a slow transport of water vapor, which has a time scale over half a year, from the tropics to the extratropics. That is really what we found in our earlier experiments, that we could start out here, everything would look good for a month or two, but after half a year, then you would start to get things in extratropics which would start to affect radiation and the temperature and temperature scores, forecast scores. So that's really the reason why we were very conservative with this. But now, I don't know what the situation is. Our model has changed since last time we did this, so now I'll just let this run for half a year and see what happens. So I'm not suggesting that we're going to do this operationally, but we're just curious to see what the situation is today. It may be that we need to do some slight tunings where we tweak the errors, but otherwise that's the situation, so it's not really simple to turn them on. Okay, I think that was it. Leave it the previous one, that was the boring one.
Right, thank you. So, before I ask questions, I should just point out for those on the phone, I hope you managed to follow along. Michiko did put the presentation on the calendar. If you didn't, I'm glad to announce this whole thing's been videoed. So expect to see it on your favourite YouTube channel in the near future. I think Elias gets to say whether it can go or not. But so, does anybody have any questions? Well, I have a comment. So, I mean, this obviously we've already spoken today, but this last example you're showing, is there any? There's not really any way to know whether this is a. Is this just could the direction of this perturbation have easily, just as easily gone the other way when you consider the bias correction interaction with this?
In principle, yes, I think so. I think it must depend a little bit on the balance of bias correction of upper tropospheric channels, water vapor sensitive.
So if we were to if you were to, so in this case one experiment going the right way is not necessarily indicative of it actually doing the right thing.
Absolutely not. It's and even worse than that. I guess over time, let's say we switch out satellite instruments, some channels get bad, we get new instruments, the picture may change. I mean, we do have some new developments in bias, in variation bias correction, so that we try to have an overall anchor so that channels, let's say, so that we're not sensitive to one instrument going out. We still try to keep the bias correction so that they are zero bias correction with respect to, at least, I mean, not here, but further up at the model top, where we've got the anchoring channels. We try to make sure that they somehow, on average, are zero, the correction for those.
So that's like AMSUA channel 14.
But what I want to say is that sort of filters down, cascades down. But that may be quite a weak effect in the upper troposphere. So, yeah, it could. I wouldn't bet on this going in the same direction if we were done on another year.
Yeah. I know people in the past have tried to anchor the upper tropospheric humidity channels for Yazi, for example, and it never went well. But there's been a number of cases where the O-Bs of those channels have resulted in highlighting model errors that were then fixed.
Yes.
So that's the other. Okay. Sorry, I'm talking. Anyone else?
How would this interact with the weak constraint formulation, or is this too small of an amplitude for it to start playing in the model airframe? Because it's now back on in operation in the stratosphere.
Well, it's our current modular formulation. It starts about here, modular 46. So it's not really doing much there. But we are experimenting with having it on. So let's answer the question with having it being on. I think it could affect it. But what we know about the model error is that in many areas you need to spin it up for several months. So I guess such a situation would be a part of that spin up. So I would not be comfortable until I had seen half a year at least of spin up. So this would definitely play into the model error spin up, I would say.
So, issue for the Irma, right? Around the Irma, the humidity increase or not? You have a sign. So we have slides, so maybe you can verify against the job site. Like this one, we have slides around the hurricane.
You can, but you cannot verify the errors against drop zones. That is.
Yeah, we will verify either you add too much or too less. For the error.
I think there are too few drop zones really to verify that. Actually, the drop around tropical cyclones is very difficult because our models and analysis resolve things quite well. So that means our uncertainty in location may be of the order of, let's say, 100 kilometers. Okay? Even analysis, we may have 50, 80 kilometers.
So you have the 18 kilometer resolution, right?
Yes. So, but you have a feature, and the feature itself is maybe, I don't know, 100 kilometer wide. And you're up to 100 kilometers. So then when you verify against observations, you've got this double penalty really, that it looks horrible against observation actually. Then you've got these small features. I mean, it's not necessarily bad to have a tropical cyclone a few kilometers off, but if you try to verify it against radiation, it may look pretty bad, I think.
So, so this year we have a H4 model.
Yeah.
They really have the jobs on the real-time assimilation system. So we can compare that
Yeah,
community against the global model. So what's the big difference around the hurricanes?
Yeah. No, we do have drop zones as well. We do assimilate those. But
So that's extra flights.
yeah, there are a lot of extra flights, and we're quite thankful, I think. Yeah. But because of the location differences between the background and the observation, we often have to put a lot of representativity errors on
The weight.
yeah, so we reduce the weight of these observations quite a lot.
Right.
We need to do that.
You mentioned, well, you showed the balance of the moisture in the clouds.
Yes.
With the other variables. You said that you're working towards using the clouds in the analysis to control bacteria.
Yes.
What are the plans for observations to use for that?
This will mostly be microwave, which is sensitive to water, liquid, and ice.
Mm-hmm.
So
Just, at least initially, supporting just microwave.
yeah, I think that's the primary.
And then you would have that included in the radiant transfer equation, the whole
That is already included. I mean, the way we do the operator at ECMWF, it's almost a plug-in. So at the moment, the observation operator works like this. Let's talk in the linear sense. So we take in temperature and water vapor column, and we split that diagnostically into cloud, liquid, cloud, ice, and then we make a diagnostic calculation of precipitating species for that column. Now, if we have cloud liquid and cloud ice transported in a tiny linear model in addition, then this gets simpler because you will have cloud liquid, cloud ice, water vapor, and temperatures input. So you don't need to do a split between from water vapor into the three species, or actually reinvent them from there. So it's just going to make life a little bit easier for the observation operator, I think. And also, it will make the connection between observations at different times a little bit cleaner, I think, because even in a joint variable, the signal from later observation will be transported better if it is now sensitive to ice or liquid and get into ice or liquid variable, and then we have that updated state, and that updated state sees another ice or liquid variable, and they can somehow balance each other out. That's the idea. Theory. Practice, we'll see.
But in practice, for a long time, you've used the microwave, cloudy microwave data, but it hasn't really fed back directly into cloud variables.
That is
at this
true.
point.
That is true.
And so that's a big step.
I think so. But I think, John, it's always like this, that we are getting slightly more accurate systems, and we are getting sensitive to things which we could get away with before. I think that's the story.
Okay.
So I have a question. Currently, you implemented this into global model, right?
Yes.
You also show the hurricane case. If you consider to use the meso-scale model or some fine-scale forecast model, if there's a constraints or the relationship we need to modify or, you know?
Well, if you look at, there is a Canadian, was it Svack and others, Luc Filion and others, they looked at a diabatic balance operator in the context of a mesoscale model. It's quite complex. I mean, they include all effects. Well, lots of effects. I still think that you can do these kind of things, even in a mesoscale model. In fact, the original paper from Asai in 1965, it did this kind of thing, was just a front model, very limited model over Sea of Japan. So, because what we're doing here, we are just taking into, let's say, first order effect. There is condensation, there's always going to be condensation and evaporation. Then it can become more and more advanced. But always you have to err on the side of being, let's say, conservative and don't take into more complicated effects which can, let's say, make things just worse by, yeah, you get too sensitive to things. So I think this effect is quite robust, at least. Convection would be an example where things would start to become really sensitive.
Okay, any more questions? Oh, one more question in the room.
Sorry. So, like our desert region, how much you added from the symbol error?
Oh, when we have the same
Against
everywhere.
climate?
Okay, let's
Like
let's-
Arizona, US.
let's show them a desert.
I'm trying to find a map.
Okay.
That one?
Let's go down, further down. One down. There's the desert. Yeah, so when it comes to the variances, it's 100% from the ensemble.
Okay.
When it comes to the length scales and vertical correlations, on the small scale, it's 90% from the ensemble. I say small and large scale because we work in wavelet space. So we do the analysis waveband by waveband. So for the low wavebands, we are working on a coarse grid, and we mix in 70% of climatology. We could probably do less now, and we are experimenting with doing less of that. But then when we go to higher wavebands, we got more samples per our 250 by 250 kilometer grid box, which we are averaging over. And there, when we go to the TR309 resolution, which is our operational highest resolution in the loop, it's actually 93% from the ensemble. So it's a mixture in, as a function of spectral wave number, how much you take from the, or spectral waveband, I would say, how much you take from the errors of the day. And of course, when we extrapolate down to wave number infinity or whatever, the variances, that is completely from the day. So it's all logical waves. But there is a question which we're asking ourselves, how much do we need of the climatology and why do we need it? So that is something which we're looking into. It's not clear to me that we need it at all. I'm doing experiments now completely without it. But we'll see.
Any more questions in the room? Don't be shy. There's no internet to go back to.
You don't know me.
Actually, I don't know. Is there anybody on the phone? Silence on the phone. Okay. All right. Well, if anybody wants to join us for lunch, now is a good time to come and ask. And let's give Elias one more sign of appreciation. Right, thanks everyone.
They still can speak on it.
What?
I wouldn't put it that way. Is there anyone on the phone?